So we've used normal force for a while now, right? As soon as we started talking about different forces acting on an object, you had your weight pointing down, you had your normal force pointing up, canceling it out because of Newton's third law, also his first law. And then we started talking about friction, and that's involved in finding friction. If you want to know how much friction there is on an object, you know how hard a surface is pushing back against it, okay? But so far we've dealt with a very simplified case where something is either sitting at rest on a horizontal surface or is being pushed horizontally along a horizontal surface, okay? When we start dealing with other situations, our normal force becomes a little bit harder to find, all right? The process will still be roughly the same, but we need to think about additional forces on our block up and down, okay? So, if we've got a block just sitting somewhere, right? This is a situation we've dealt with before. There are two forces acting upon this object, all right? It's at rest, which means that the two forces acting on it need to be canceling out, okay? So if we have some weight going downward, we will also have some normal force of the same size going upward, and they will be equivalent. Okay, so when we're looking at a block just sitting on the ground, Fw is going to be equal to Fn. All right? In other words, we could just do mass times gravity to find our normal force. Okay? Very simple case. If we're looking at a block being pushed horizontally, okay, again, we'll have a downward force equal to our weight. All right? And we may have some side-to-side forces. Let's say that we have an applied force and maybe some friction force against it, okay? Those two side-to-side forces have no impact on the normal force, all right? Because the definition of normal force is the force perpendicular from a surface. Okay, so if we're actually looking at this surface here, it's horizontal. That means that our normal force will be vertical, okay? It doesn't care about the side-to-side forces. The surface is not counteracting those, okay? What it does try and counteract is the weight. And so long as this thing isn't accelerating into the ground or accelerating up into the air, those two forces have to be canceling out due to Newton's first law, okay? So our normal force going upwards will again be equal to our weight. Okay, so if you've got something on a horizontal surface and the only vertical forces on it are weight, then that means your normal force will be equivalent to your weight, okay? But if you're dealing with additional forces, like if I had an object sitting on a desk and then I pushed down on it additionally, it still isn't accelerating through the desk, but there are additional forces pushing downward that the normal force has to counteract, okay? So with this one, we'll have our weight going down, and let's say that we also have an additional applied force going down, okay? This thing isn't going through the ground, so that means that our normal force must be large enough to counteract both of those, right? Large enough, but not too large, right? If your normal force was larger than the sum of those two, it would be accelerating upwards. So what we can say is that we'll have a normal force pointing up, and it will be equal to the sum of your weight and your applied force, okay? Another way that we can think about this is in terms of net force. Like where this formula actually comes from is in the definition of net force. So net force is the sum of all the forces on a block or on an object, okay? We've got our weight pointing down, we've got our applied force pointing down, we've got our normal force pointing up, okay? Adding all of these together gives us our net force. Because this thing isn't accelerating up or down, that means that our net force has to be zero, according to Newton's first law, okay? So if the sum of all of these is zero, what we basically end up getting, moving it around, right? If we want to solve for Fn, we would subtract both of these over here, or we could just subtract Fn over and leave everything else over there. Okay, we get that negative Fn equals Fw plus Fa, which actually does point something out that was kind of left out from the original version of how we were writing this relationship. Fn is going to be in the opposite direction, okay? If you've got your two forces pointing downwards, your normal force will be pointing upwards. Okay, it will be in the opposite direction. That's what that negative means. Okay, if we wanted to make them numerically equal to each other, we would need to flip the sign on our normal force. Okay, this is more talking about the magnitude of those forces, not the directions. All right, the size of your normal force will be equal to the sum of your two other forces. All right, so now let's look at a block being pulled up. All right, we've got our weight pointing down. Okay, but this time we've got some applied force upward. Okay, let's say that it's not enough to actually lift the object, right? Like a 100 Newton object, and you're only lifting up with 10 Newtons. Okay, the desk wouldn't need to be pushing up as hard because part of that downward force from your weight is already being canceled out. Okay, so if you think about like when you're in an elevator, all right, as you're being pulled up or pushed down, you feel lighter or heavier based on how hard the ground has to push against you. Okay, when we're looking at our normal force here, total, our net force still needs to be 0. Okay, so all of our upward forces needs to equal all of our downward forces. Okay, so we're still going to have a normal force on here, but it will be smaller than your weight. Okay, the sum of all of your upward forces, Fn and Fa, because this thing's net force is 0, will be equal to any downward forces. Okay? All right, and again, we can solve this thing looking at Newton's first law, like what F net is. Okay, so your net force is the sum of all of your forces, where you've got your weight, you've got your applied, and you've got your normal force. Okay, so if F net is 0, if this thing isn't moving up or down, okay, we've got these two in the same direction. So let's leave them on the same side of the equation, moving Fw over to the other side. All right, we end up getting that Fw, negative Fw, equals Fa plus Fn. Okay, we've brought all of our downward forces to one side of our equation, and we've got all of our upward forces on the other side of our equation. Okay, and you got that negative you got that negative in there again, which is basically saying that your weight will be in the opposite direction from your applied and your normal force in this case. Okay, so with the positives and negatives, when you're trying to figure out which is which, decide ahead of time. Do you want down to be positive? Do you want up to be positive? As long as you're consistent as to which direction is which, the numbers will end up checking out. Okay, so if you've got to figure out the normal force for something where something's being pushed down, look at the sum of all your downward forces. Your normal force will be equal to that. Okay, if you've got something that's being pulled up, the sum of all your upward forces will be equal to the sum of all your downward forces because it isn't accelerating up or down. Okay, so if you've got a net force of 0, set your upward stuff equal to your downward stuff. Right? Think about what directions things will have to be pointing. We've got one more case where we've got a block being moved at an angle. Okay, so let's just erase all of this and let's get a block at an angle. Cool. So let's say that we've got a block, and how about we're pulling it up and at an angle? So like this. Okay, we've got some angle. All right, and this is our applied force. Okay. If we look at that, we can break it into components. Okay. Part of this force is pulling to the side. That has no impact on your normal force. Okay, that's an applied force horizontally. Your normal force will always be perpendicular to your surface. Okay, so because this is horizontal to it, it doesn't need to cancel it out. All right, your normal force is really only concerned with any upward or downward forces. All right, so looking at the forces on this block, we've got our weight pointing down, Fw. All right, we've got an applied force off at some angle, and we've got our normal force pulling up. Okay, our total up and down, because this block is staying on the ground, not accelerating up or down, our total force on this block needs to equal 0, at least vertically. All right, we may have some side-to-side forces. That has no impact on your normal force. Okay, so if we're looking at this, basically what we have is a downward force of our weight, okay, and then 2 upward forces. We've got the normal force from the surface, and we've got the vertical component of this applied force. Okay, so your weight will be equal to your normal force plus the vertical component of your applied force. Okay, and to find that, well, let's look back at components. Okay, we've got an angle, we've got a hypotenuse, we're looking for the opposite side, so you would use sine to figure out how big that vertical component is. Okay, so when we're looking at normal force, really all we care about are forces that are perpendicular to your surface. Okay, if you've got downward forces, normal's going to be trying to cancel those out. If some of that downward force has already been canceled out by some upward force, then your normal force doesn't need to be as big. Okay, let's draw another one. One more where it's at an angle. Okay, because it's not always going to be pulling upward. All right, you may have downward and at an angle. But the same thought will still work out, where you set your upward components equal to your downward components. Okay, so we could have a block that is being pushed downward and at an angle. Okay, some applied force down there. Okay, so looking at all the forces on here, we'll have an applied force downward at an angle, and you'll have a weight going down. Okay, if this block isn't accelerating downward, then that means all of our forces have to be balanced out. Okay, so our side-to-side forces have no impact on our normal force. All right, but vertically, we have our weight pointing down, and we have the vertical component of our applied force. Okay, your normal force, if this thing isn't accelerating up or down, would need to cancel out both of those. Okay, your upward and downward forces are equal in this case because it's just sitting on the ground. It isn't accelerating upward or downward. Okay, so in this case, our normal force will need to be equivalent to all of our downward forces. The sum of all our upward forces will equal the sum of all our downward forces. We've got Fw plus the vertical component of your applied force. Okay, so that thought kind of works with anything on a horizontal surface. If you've got vertical components or vertical forces and it isn't accelerating up or down, basically you're saying my net force is 0. So look at all the forces that you have pointing up or down and set them equal to each other. Okay, any upward forces will have to cancel out with any downward forces if your object is not moving vertically. All right, that ought to do it. All right, so there are some components and stuff in here, so still think triangles. It always helps to draw diagrams, and if the wording on the problem itself is ambiguous, make sure that you send me a message so I can send you a picture of what I was talking about. All right, see you later.